Okay, now we're going to topic 3, two-dimensional motion. In two-dimensional motion, we pretty much make use of information that we learned before. So there's really nothing new in this topic. It's just put in together, um, putting things together. Two-dimensional motion is just like a football being thrown through the air, right? Um, like Thad Lewis throws a touchdown to, um, say, Eric Wood, right? And that ball leaves his hand. As it leaves his hand, it travels through the air, um, both in the X direction and in the Y direction. So as before, we were only looking in one direction, whether it was X or whether it was Y. Um, in this case, we're looking in both dimensions. And you can imagine yourself playing catch in the backyard with your friend and throwing the ball back and forth to each other. And the ball travel up to the person waiting over here. And so this ball has movement in both the X direction and up and down in the Y direction. So it's both X and Y. Um, the vertical component is influenced by gravity. So the up-down part, this part here of that movement is influenced by gravity. And its acceleration is minus 10 meters per second for every second, or minus 10 meters per second squared. The horizontal component is not. If you take air resistance out of the equation, which we will do during this topic, then there's no acceleration in the x-axis in the x direction at all. So you can think of it sort of like, let's just take only the x direction, like a puck. If you take, there's obviously a little bit of friction, but if you ignore that and you shoot a puck, then that puck's going to travel along on ice, and it's going to keep its speed. Its speed is not going to change if there's no friction until it hits a wall or something. So the same thing will happen with a ball traveling through the air, or anything that's being thrown through the air has no acceleration in that direction. So the speed will just stay the same while it's in the air. So what that means is while you're traveling in the x direction, it depends on the time. But in the y, as we saw from last topic, it depends on time squared, which makes the relationships parabolic. So this sort of upward and downward movement is a parabolic relationship to the squared. We already know how to do both horizontal, and vertical problems. So the only adjustment is putting this together. And we're going to organize it still using a really good chart. And this helps out because what we do for this case is we have a double one, where we have the x direction, but we also have the y direction. this will be our new really good chart for the first part of this topic. We'll add this to our content as well. Okay, so we make use of that, but we'll consider these separately. We'll consider the movement in the x direction and in the y direction, and we'll break those apart separate. So we take plus x and plus y, minus y down, minus x to the left. Now, things like balls or bullets move through the air differently than planes, birds do, because the birds, or a rocket, okay, because those have a sense of propulsion through the air, those birds, the plane, or the rocket. So, and they can steer themselves and make changes and move around. Whereas the ball or the bullet, once it's fired, it travels throughout, and it travels, and but it's only under the influence of gravity. Okay, so they cannot steer themselves. They can't adjust their speed willfully. They have to go by what they are. You decide how hard to throw a ball, but once that ball leaves your hand, then it's out of your control. It's under the influence of gravity. We call these helpless objects projectiles. Okay? And the path that they take, we call trajectory. So the projectile can travel through the air below in a trajectory. This right here, its path is the trajectory, and this we call the projectile once it's launched into the air. We call its highest most point that it's reached the apex, okay, of its flight. We take, in this topic, we'll take each of these masses that are traveling through the air as point masses. The air moving will not slow them down, okay? There's no surface area. That's how we look at that. And a lot of things actually do model this type of movement. Okay. We can see that this is a picture that will help us see that in the y direction, it's under the influence of gravity. So we have two balls here. One ball is dropped straight down, whereas the other ball is shot out in the x direction. And the first thing to look is in the x direction, which is like this. We can see that each time that the ball moved, in each x movement, these two, so we have the x direction, and if we take the middle of these balls, we can see that each time, oh boy, oh yeah, try to move them together, that the balls have moved the same distance in the x direction because there's no change. Oh boy, that's frustrating. I wonder if I lock this in place. There we go. So I can see if I go to the next, well, the next time it moves from place to place, we go down, it still moved the same amount of distance in the x. So each of these movements in the x are the same each time. So this ball's been shot out, and it's just like rolling along a desk. It's the same amount of distance it moves. The speed doesn't change in the x direction. In the y direction, the speed does change. However, we can see another interesting thing. The ball that's just dropped is in the same place as the ball that was shot out. Okay? So this means, like, if you were to fire a gun exactly horizontally, and as the bullet left the muzzle, another bullet simultaneously dropped from the same height to the ground, both of those would hit the ground at the same time, even though the one bullet that was fired out of the muzzle was traveled a much farther distance horizontally. They would still land if the terrain was flat at the same place. So in a photograph, it shows the two balls being released at the exact same moment. The left ball is dropped from rest, and the other is shot horizontally. Both balls have the same vertical position for each flash of the strobe light, and that this means that the balls will each reach the ground at the same time. Okay. So 3.1, we'll look at that motion that's sort of modeled in that photograph. And we'll call this half parabola motion. So there's no real up part, just a down, or half parabolic motion. We get to treat x and y independently. It begins with a vertical initial velocity of 0, okay, and some horizontal velocity. You can think of a lot of situations that describe this. A ball rolling off a table, or a car driving over a cliff. Those are examples of half parabolic motion. So we'll get right into an example with this. A car moving at 22 meters per second drives off a 40-meter tall cliff. How far away from the base of the cliff does the car land? So in this case, we have this car sitting up on this cliff, and the distance, the height of the cliff, is 40 meters to the floor below, and the car is driving at 22 meters per second, like that. Okay? Well, when we do that, we can get out our chart here. Shrink it a little bit. And we have the x direction and the y direction. Now we know information already that we can fill in. So first off, horizontal speed in the x direction, or Vx, is equal to 22 meters per second initially. And for the whole flight of it, till it crashes to the ground, it keeps this speed. It does not change. The horizontal stays the same. So all those are 0 right off the bat. Vertically, we know our original speed is 0 in the vertical. We don't know the final speed. We do know the height of the cliff vertically would give us a minus 40 meters because that's how far down in the y direction we're going to move. So you see how we're breaking these up into y and x directions. Now the nice thing is, the thing that links these x and y, since it's the same object, is the time. The time is the same. in the x and in the y, since it's the same object traveling. So we also know what a is in the y, since it's accelerating due to gravity. So this means that we can go ahead and find our, our final speed in the y using a very similar equation that we used last topic. Vf squared equals Vi squared plus 2a delta s. So Vf squared equals 0 squared plus 2 times minus 10 meters per second squared times minus 40 meters. That gives us Vf squared equals 800 meters squared per second squared, which gives us a velocity, if we take the square root of both sides, 28.3. It's going to be the negative since it's moving downward, meters per second. So in the y direction, we have this 28.3 meters per second. Now I can see that the average speed would be 14.1 minus 14.1 meters per second. Delta V would be Vs minus Vi, or minus 28.3 meters per second. And delta T is delta V over A, or minus 28.3 meters per second squared, over minus 10, meters per second, over minus 10 meters per second squared, which equals 2.83 seconds. So that's how long it's in the air. And that 2.83 seconds is the same up here in the x direction as well, which allows us to be able to calculate delta S from V bar is delta S over delta T. So delta S equals V bar times delta T. V bar is 22 meters per second in the x direction. Delta T is 2.83 seconds, and that gives us 62.3 meters. Now that means, the question, if we go back here, says, how far away from the base of the cliff does the car land? And our answer, 62.3 meters from the edge of the cliff. Okay, good. So that's a half parabola problem. You can see it's all stuff that we've used before. It's just putting the two together. So that really simplifies analyzing and solving problems that are half parabolas. All right, in our next problem, a marble rolls off the edge of a table and lands 60 meters away from the base of the table. We want to know how tall the table is. So to do that, let's start with a picture. We have our table top. We have our marble rolling off the table. And hitting the floor below. It says land 60 centimeters away from the edge of the table. And it was rolling at V equals 2 meters per second. Well, let's see what we can fill in here. All right, so in the x direction, you can see that our original speed is the 2 meters per second. Ask yourself how that will change in the x direction as it travels. It will stay the same. So those are all 0. In the y direction, we still have a negative downward acceleration. We don't know anything else except, well, VI is 0. It's rolling off the table. We don't know anything else. But we have the 60 centimeters. Well, that should relate to be able to give us our delta S and the x. It's positive, and it's 60 centimeters. So if we convert that 60 centimeters to meters, so we're in the same units as the 2 meters per second and the minus 10 meters per second squared, we know there's 100 centimeters in 1 meter, so that will give us 0.6 meters. And that's our distance, or our displacement in the x. Well, the thing about this now is that from what I have in x, I can get this last piece, a delta t, because we know v bar is delta s over delta t. So delta t would be delta s over v bar, because we'd bring it up and then divide by delta v. And delta s was 0.6 meters, and v bar was 2 meters per second. So that gives us a time of 0.3, of course, seconds. If you remember, that's the same as the time in the y, since it's the same marble that's going in the y is going in the x. So now we got a and delta t in the y, and you might remember this equation, Vf equals Vi plus a delta t. And so Vf would equal minus 10 meters per second squared times 0.3 seconds. So if we start at a speed of 0 and we fall for 0.3 seconds with an acceleration of 10 meters per second squared, it makes sense we'll fall and we'll be traveling at minus 3 meters per second. After 1 second, we would have been going 10 meters per second. With only 0.3 seconds, we'll be going at minus 3 meters per second. So v bar would be minus 1.5 meters per second, and delta v would be minus 3 meters per second. That makes sense for our time, too. Now I can get the height of the table because I can just use this equation again, but in the y, where delta s is v bar times delta t, and v bar was minus 1.5 meters per second, and delta t was 0.3 seconds. So 0.45 meters, or minus 0.45 meters. That goes in here. So the height of the table is 0.45 meters, or 45 centimeters. Well, that's one short table, but other than that, you can imagine kids playing marbles, so I guess that makes sense. And that will take you through 3.1.